We're asked to prove a triple angle formula. In fact, it's an identity, so I'm just going to change that equals to having three lines. Right, now there's an addition formula for sine. Sine A plus B is sine A cos B plus cos A sine B. So to make 3x, we can set A equal to x and B equal to 2x, which means that sine of 3x will equal sine of x cos of 2x plus cos x sine of 2x. It is worth knowing your double angle formulae off by heart. So cos 2x is 1 minus 2 sine squared x, and sine 2x is 2 sine x cos x. Let me just derive these. The second one actually comes from this formula here, but letting a equal to x and b equal to x. So then we get sine 2x is sine x cos x plus cos x sine x. You can see that, sorry, these are all identities. And then we get 2 sine x cos x, as I said. The other one comes from the addition formula for cos. Cos a plus b is cos a cos b minus sine a sine b. So if we set them both equal to x here, we get cos of 2x is cos squared x minus sine squared x. Replace cos squared x by 1 minus sine squared x. And then we get the result. It's worth becoming just used to being able to get all three. So there's cos squared minus sine squared, 1 minus 2 sine squared, and 2 cos squared x minus 1, because you use them in different places, as well as becoming familiar with the sine 2x one. All right, so let's keep going. I'm now going to multiply, well, let me just tidy up. So sine x times 1 minus 2 sine squared x plus 2 sine x cos squared x. But I'm going to now replace that cos squared x by 1 minus sine squared x. Therefore, I get sine x minus 2 sine cubed x plus 2 sine x minus 2 sine cubed x, which gives 3 sine x minus 4 sine cubed x, as was required. Good. Moving on, we've got a couple of integrals to take a look at. And you can see that immediately we've got a sine 3x. We're probably going to be using the identity that we've just derived. So I can rearrange this identity to give 3 sine x minus 2. Sorry, uh, let's make 4 sine cubed x a subject first of all. So 3 sine x minus sine 3x is going to equal 4 sine cubed x. Because we can now see it's very similar to this. I just need to double it. Double each term. We get 8 sine cubed x. So often double angle formulae and even triple angle formulae can be used to help integrate things like sine cubed x or sine squared x. But here, because we have this power of 2 over 3, we actually want to get it back from the triple angle formula to having sine cubed x, because we can raise that to the power of 2/3 more easily. Therefore, this becomes cos x multiplied by 8 sine cubed x, all raised to the power of 2/3. So 8 to the power of 2/3 is the cube root of 8 squared. Cube root of 8 is just 2. 2 squared gives 4. And then sine cubed, well, we basically just times the powers together here because it's in the form y to the a all to the power b. So it just becomes y to the ab And then 3 times 2/3 is just 2. So 4 sine squared x. Just going to rewrite that. I can even bring the 4 out of the integral. I'll write it as sine squared x cos x. Now you could do a substitution here, u equals sine x, and it will work out, but ideally you want to be using integration by inspection. Let's do a trial function. If I differentiate sine cubed x, because look, I can see that I've got the derivative of sine x right here. So when I differentiate sine cubed x, I use the chain rule and I bring the power down and I lower the power, and then I times by the derivative of the inside, which is sine x, and I get my cos x. Because I'm aware of that, it's going to be a much easier to then integrate things involving things like sine to the n, x times cos x. So this is simply going to become 4 times, now I just need to modify my trial function and divide by 3. So it'd be 1/3 times sine cubed x. Because now when I differentiate it, the 3 and the third cancel, I lower the power, times by the derivative of the sine, it all checks out. Don't forget the plus c. And then finally, it's just going to be 4/3 sine cubed x plus c. So nice result there. One more integration to do for part C, this one here. So this time when I did this one, I couldn't quite as easily see the identity because of this term. And we've got a 3 sine 2x in there as well. So I decided to do 2 cos x. Remember, we're raising the whole thing to the power of a third. So I replaced sine 3x by the formula that we've derived. So 3 sine x minus 4 sine cubed x. Okay, remember, we're still raising it all to the power of a third. Right, that, I think, is the identity bit sorted. So 3 sine 2x minus 6 sine x cos x plus 8 cos x sine cubed x, all raised to the power of a third, dx. Now this looks not very nice at all until we recognize that this actually is simply also 3 sine 2x. Remember that identity I had before, that sine 2x was 2 sine x cos x. So 6 sine x cos x is 3 sine 2x, and these cancel. This therefore becomes 8 cos x sine cubed x raised to the power of a third. And I can raise each one to the power of a third separately. So 8 to the power of a third is 2. Cos x to the power of a third is simply going to become cos to the third x. Nothing we can do about that. And then we get sine x. Don't forget, still haven't actually integrated yet. And now I can do another kind of inspection. So with sine to the nx cos x, then I raise the power by 1 on sine. Now I'm going to do very similar for cos. So I'm going to try and do d by dx of cos to the 4/3 after I've raised a third by, I've added 1 to a third. Then I bring the power down, reduce the power, just like we're doing the chain rule here, but a function of a function. Because remember, this is actually cos x to the 4/3. So the outside function is something to the 4/3. So that's why I've gone and done that. And then times by the derivative of the inside, which in this case is minus sine x. So I get minus 4/3 cos to the third x sine x. So all I need to do, I've got my 2, is times by minus 3/4 to cancel that out. Because if I put a minus 3/4 here, then they would ultimately cancel out and I would get cos to the third x sine x by itself. and I just need my plus c, which overall is going to give minus 3 over 2 cos to the 4 over 3x plus c. Okay, a nice set of integrals. Well done.